Welcome to the course on Introduction to Electrical Engineering. We will discuss on lecture 12 today on single phase AC circuit part 2. To start with the outline of today's presentation, we start from introduction, then we will go for single phase AC circuit, in which we will discuss a steady state AC response for pure inductive circuit, then we will discuss a steady state response pure capacitive circuit, then followed by steady state response for series RL, RC and RLC circuits, and then we will take of course exercise as numerical analysis. So, coming to the introduction of this part of single phase AC circuit. So, we are having here electrical component which are part of this. Active components are voltage and current, voltage source and current source, and passive component are resistor, inductor, capacitor, and this chapter deals with the steady state response of circuits with sinusoidal forcing function applied to the passive elements like R, L and C and their combination like. So, the typical example for resistance based circuit at utility power level are typically used for heating. Here you can say where the applications where AC is applied to the resistive circuit, typical electric iron uses or electric iron or press uses a resistance coil to generate heat, power loss and of course, power through the AC. Or normally we have AC supply, and the another example is typically your electric heating system. So, electric room heaters use resistivity coil to produce the heat powered through AC or AC power. Then the typical example is here where we have electric heating, or you can call it electric geysers with heating element, resistance based powered again powered through AC supply. Then we have here the electric heating through inductive coil used for powering through the high frequency AC supply. An application is where AC is applied to inductive circuit like, and with the AC source it goes to some time AC to DC, I mean like, and then DC to AC inverter, then matching transformers with the induction coil, and of course, we have magnetic flux which gives to the work force, and we have a temperature sensor which controls the temperature of typically for induction heating element or and give as a feedback to the converters like. We have of course, the transformer, I mean like single phase transformer. So, where AC is applied to the typically to maybe we have like a as a RL load, because it contains consists of RL elements, like you have a typically reactance of the transformer as well as the resistance of the transformer windings, as well as the representing the core loss in the transformer, as well as the exciting current and is represented by the your typically a kind of equivalent circuit with the help of this magnetizing reactance, and of course, with the various component of leakage reactances like. Then the another typical example which is powered by AC power supply is the single phase permanent brushless DC motors, which are typically used in many applications like fan, maybe like a exhaust fan, ceiling fan, even a cooling fan work on single phase, like a cooling fan typically in the computers or in many such appliances. Then of course, you have a single phase induction motors, which contains of course, RL as well as C component used for normally to give a phase shift for the purpose of starting, as you can see the circuit here, and work on single phase supply used and normally used for pump, fans, compressor application. Now, coming to steady state AC response for AC for a pure inductive circuit. So, we have here typically a single phase supply applied to pure inductor. So, effect of sinusoidal current flowing through a coil, and here we can call it inductance of this inductor is L Henry, and it has negligible resistance just to explain the phenomena. So, coming to now waveform of current and rate change of the current and the induced EMF. I mean, you have a like a current, and then we have a typically a rate change that is shown like a black shaded portion, as well as we have a induced EMF here with the again line with the blue shaded portion. So, we can say first quarter cycle of this, because of the symmetry will analyze. So, quarter cycle has been divided into 3 equal intervals like OA, then AC and then CF in seconds like. So, here we can say the interval OA, the current increases from A to B, I mean like going to be from A to B, and then average rate change of current will be A B upon OA, that is AB is the vertical portion which current increases and O is the time period. So, we can say it is ampere per second, and the value is represented by J K in ordinance drawn by the midway of between O and A here in the rate change of the current. And typically induced EMF in volts induced in a coil is L into rate change of the current, that is d I by dt in terms of ampere per second, and that is the voltage, you can call it like go to the point Q, that represents the E here. The average value of the induced voltage during interval is O A and is L into A B upon O A. And this interval A C, the current increases from A B typically from to C E, and average rate of change of current is D upon A C, that is D upon the period A C ampere per second, and it is represented by ordinate L M. L M typically here in this in figure, and induced EMF is L into L M in volts and represented by L R from here to here. Well, in interval A C, that is virtually the current increases from A B to C A, and average rate change of current is G H, typically G H upon C F from here to here, and namely N P is the ampere per second, and induced EMF is L into N P volts and represented by typically the your N S for the third interval. So, at instant F, the current has again ceases to growing, and rate of change of the current is then 0 typically on the point here, and induced EMF also decreases from maximum O point to the typically value of 0 at F point here. So, curve can now be drawn through the derived points as shown in figures, and we can say during the second quarter cycle the current decreases and rate change of the current is negative typically here, and induced EMF also becomes typically kind of negative. So, since wave of the current is symmetrical about ordinance F H, so the curve representing the rate change of current, I mean induced EMF in the coil will be symmetrical with those derived with the first quarter of cycle, and the rate change of current at any instant is proportional to the slope of the current wave at instant. So, induced EMF increases from 0 to F typically at to a maximum at T typically here as you can see in magnitude, and induced EMF decreases to 0 at again point at U T here as you can see, and by using the shorter interval for the example taking a ordinate at 10 degrees, the trigonometric function to derive the fairly accurately the shapes of these curve, and you can take a voltage and current waveform for pure inductive load. Here you have a typically the voltage and current, I mean this is the current waveform and this is the voltage waveform, that is represented by typically of E also because it is a pure inductive load. And you can see the current is peak at the 90 degree where the induced voltage is applied voltage or induced voltage is 0 at that moment. So, resistance of the coil is considered negligible and applied voltage as being the induced EMF, and since the later is sinusoidal, the wave of applied voltage must be also be sine wave. So, typical here the applied voltage attains its maximum positive value at a quarter of a cycle earlier than current. So, voltage applied to the purely inductive leads the current by a quarter of a cycle or that 90 degree, and if there were no current there will be no flux and therefore no induced EMF in the coil like. So, the voltage current waveform of pure inductive circuit can be presented here. I mean typically suppose instance value of the current through the inductance L Henry and negligible resistance present here. So, I equal to I m sin omega t, that is I m sin 2 pi f t, where omega is 2 pi f t here, I mean as shown in this waveform, and you can say instance value of the induced EMF will be E equal to L d I by dt equal to L I m. We can take a derivative of d I upon dt sin 2 omega t, that become 2 pi f L I m cos 2 I f omega 2 pi f t, and that we can write E equal to 2 pi f L I m sin 2 pi f t plus pi by 2, just phase shift of 90 degree, and since f represents the number of cycles per second. So, duration of one cycle is 1 upon f second. So, where that at t equal to 0 cos 2 pi f t equal to 1. So, induced EMF in the coil is 2 pi f L m, that is the maximum here, and where t equal to 1 upon 2 pi f. So, cos 2 pi f t equal to cos phi, that is minus 1, and the induced EMF typically will be at this point will be minus 2 pi f L m on this point like. So, the resistance of the circuit is negligible and applied voltage equal to the induced EMF. So, instantaneous value of applied voltage you can call it V equal to E, and that is 2 pi f L m I m into cos 2 pi f t, and that is equal to 2 pi f L I m sin in bracket 2 pi f t plus pi by 2, and comparison of expression shows the applied voltage leads the current by a quarter of a cycle. So, maximum value of V m applied to the circuit is 2 pi f L m f L I m, that is V m equal to pi f L I m, and so V m upon I m equal to pi f L, and if I and V are the RMS value, then we can say V upon I equal to 0.70 V m divided by 0.707 I m equal to 2 pi f L. So, inductive reactance represented in ohms and resistance represented by symbol x L, and hence in this we can say I equal to V upon 2 pi f L equal to V upon x L, where x L is 2 pi f L ohms. So, now you can say inductive reactance is proportional to the frequency, that is 2 pi f L. So, as you say the inductive reactance will increase with the frequency, and current produced by the for a given voltage inversely proportional to the frequency as C, because the reactance will increase. So, denominator will increase, so current will reduce with increase with the frequency like. So, the inductive reactance is proportional to the frequency and voltage inversely proportional to the frequency as shown in the typically in the figure. So, here you can say the current is here on base and is the on quadrature to that is V equal to 2 pi f L into I. So, here we can take typical again analogy. Suppose we take a heavy metal cylinder C and roll it back and forward, and on a horizontal surface between the two extreme position of A and B, and consider the forces and the speed while C is being rolled from B, and at first the speed is 0 at A, and then the force applied to the body is reduced from A to C. Then you can call it the mechanical analogy of pure inductive circuit can be applied to. So, applied force is reduced so until it is 0 when C is midway between A and B, and C ceases to accelerate, and again it attains maximum speed from left to right. Well, that is about the analogy with the mechanical system for this typically of inductive circuit. Let us come to typically look into a response of steady state AC response for a pure capacitive circuit. So, here we have a circuit with the capacitance only. You have a AC source and we have a typically a ammeter followed by a capacitor in the circuit, where you have a two plate of capacitor D and E, and value of this capacitor is C. The alternating voltage applied to C is represented in the figure, and voltage to be positive when it makes plate D positive relative to E plate, and I equal to C into rate change of the potential difference across the capacitor. So, voltage and current waveform for pure capacitive circuit, you can say clearly here that the voltage, the typically current is leading than the voltage, applied voltage in this case of capacitance, and that will derive how it will be there. So, potential difference is increasing positively, as you can see here, and at the maximum rate at instant of 0, because that slope is maximum, and the charging current is also at its maximum positive value at that instant. So, a quarter of a cycle later, applied voltage has reached its maximum value, and at a very brief interval of time, potential difference neither increasing nor decreasing. So, that there is no current at this moment, and during the next quarter of cycle the applied voltage is decreasing. So, capacitor is discharging. So, discharge current being in a negative direction. So, voltage passing through 0 here, and the slope of the voltage curve is at maximum, and that is potential difference is varying at the maximum rate typically here. So, current is also a maximum at that instant, and in this case we start with the voltage wave. So, with capacitance that derive the current by differentiating the voltage expression mathematically to derive. So, suppose that the instantaneous value of the voltage applied to a capacitor, and capacitor C is in farads, is represented by V equal to V m sin omega t, that is V equal to V m sin 2 pi f t, and if the applied voltage increases by dV in dt second, then the instance value of the current will be I equal to C dV upon dt, and that will be equal to C dV upon dt of V m sin omega sin 2 pi f t, and that will become 2 pi f c V m sin 2 pi f t plus pi by 2. So, now looking at Phasor diagram of for pure capacitive circuit, I mean we have here the current voltage here and current is leading 90 degree. So, current will lead the applied voltage by a quarter of a cycle, and the figure and voltage can be represented by phasor in the figure. So, we can say the value of I m, the current in is 2 pi f c V m. So, it will cause the V m upon I m equal to 2 pi f c, and hence if V and I are the RMS value, we can say V upon I will be again I upon 2 pi f c. So, capacitive reactance is expressed in ohms and is represented by symbol x c. So, hence we can say I equal to 2 pi f c V equal to V upon x c, where x c is equal to 1 upon 2 pi f c. So, the capacitive reactance is inversely proportional to frequency, and the current produced by a given voltage is proportional to the frequency, as you can see here. So, as capacitive reactance, because your frequency is denominator as increasing, so capacitive reactance is decreasing and current is increasing with the frequency proportionally. Well, now coming to steady state AC response for a series RL, RC and RLC circuits. So, let us discuss steady state AC response for series RL circuit. Now, considering the combined effect of resistance and inductance as shown here in the figure, we have AC source, we have a resistance and we have a inductance, and now the voltage current here will be, you have a voltage which typically at the peak point, and current peak is certainly after little period of some time at the angle of phi, as you can see here with the blue color, and it makes typically now two component of it. I mean we have a current and we have a resistance drop in the same phase as the current, that we call it V r, and then we have a current, your reactive drop V L, which is perpendicular with the current. So, we call it V x, V L, and the sum of these two, phasor sum of these two comes as V x, V with the phasor angle difference between I and V equal to phi. So, that represents the phasor diagram for this RL circuit, I mean excited by single phase AC source. Now, coming to this phasor diagram, results from an application of Kirchhoff's second law, and the current is taken as a reference here and common to the all the element of series circuit, and the circuit voltage then may be derived from the following relation. V r is in phase with the I, and V L equal to I L is where V L leads the voltage by typically 90 degree, I mean here from the current, and you can call it V r in phase I r and V L in quadrature with the phase typically with the I 90 degree, and then V total V will be V r plus phasor of V L, and this we can represent the angle of the phase difference between D and I term as the phase angle and represented by phi, and we can here, since two component of the voltage are at 90 degree. So, we can write equal to V equal to V square plus V L square root, and V equal to I in again bracket R I square plus I r is I square x l square under root of that, and we can call it V equal to in bracket R square plus x l square under root of that, or V equal to I z, where z equal to your R square plus x l square, I mean under root, and z again we can call it R square plus omega L square, omega square L square e power 1 by 2. So, we can say here z term as the impedance of the circuit, and we can say Ohm's law also applied to AC circuit analysis, and instantaneous phasor diagram, the current lags the voltage by a phase angle greater than 0, but less than 90 degree, because it has a resistance and inductive circuit. So, phase angle between the voltage and current is determined by the ratio of resistance to the inductive reactance in the circuit, as shown in the typically in phasor diagram. So, greater the value of this ratio, the lesser will be the phase angle, because circuit will be towards more the resistive network. So, by the geometry of the diagram we can say phi will be tan inverse V L upon V r, or tan inverse I x l upon I r, or we can say phi equal to tan inverse x l upon r, because current is the common in the both the element as a series RL circuit. So, the phase angle may also be derived as phi equal to cos inverse V r upon V, or cos inverse r upon z, where phi is cos inverse r upon r square plus omega square L square to power 1 by 2. So, now coming to the steady state analysis of a steady state AC response for series RC circuit. So, effect of connecting the resistance and capacitance in series is illustrated here. So, we have AC source and we have a resistance and capacitance connected in series, and here we have of course the same kind of a concept like we have a now current leading than the voltage, and you can see here typically the resistance drop in phase with the current and the capacitive drop, of course the voltage is 90 degree lagging than the current, and net voltage is also lagging from the current like, or V is leading the current like. So, the circuit voltage is derived from the following relation. So, V r is in phase with the I and V equal to I x c, where V x lags V c lags like typically I by 90 degree. So, where V r equal to I r, V c equal to I x c, and V equal to V r sum plus V c, where V equal to again V square plus V c square to power 1 by 2, and V again equal to in bracket I square r square plus I x square x c square, again 1 by power 1 by 2, and V equal to I under root r square plus x c square, and V equal to I z volts. So, where we can say z equal to r square plus x c square to power 1 by 2, or z equal to r square plus 1 upon omega square c square to power 1 by 2. So, z is the impedance of the network, and the impedance is the ratio of voltage across the circuit to the current flowing through it, and other conditions remaining unchanged. So, coming to now instantaneous phasor diagram, the current leads the applied voltage by phase angle greater than 0, but less than 90 degree, and phase angle difference between voltage current is determined by the ratio of the resistance to capacitive reactance in the circuit. As you can see here, I mean the voltage is in phase with the current, and then the voltage across the capacitor is 90 degree lagging, and the sum, I mean net sum of phasor is equal to the V, and that follows the phasor of resistance and reactance in capacitive reactance is the typically the impedance. So, by the geometry of this diagram we can say phi equal to tan inverse V c upon V r equal to tan inverse I x c upon I r, and phi equal to tan inverse x c upon r. So, phase angle may also be derived as follows: phi equal to cos inverse V r upon V, or equal to cos inverse r upon z, and phi equal to cos inverse r upon r square plus 1 upon omega square c square is to power 1 by 2. Well, now coming to the steady state AC response for the series RLC circuit, and this combines the instances of R and L in series with the that of R and C in series. So, you have a 3 element R L C in series with the source excited by V and the current flowing into this I RMS current. So, now typically resistance R ohms, inductance L Henry, and capacitance in farads in series, and connected across a AC supply of V volts RMS and at a frequency of f hertz, and let the I be the RMS value of the current in ampere here in this circuit. So, potential difference across the R is RI volts in phase with the current, and which is represented by a phasor OA, typically here in phase with the OI in the figure, and the potential difference across L is the 2 pi f L I, and represented by phasor typically OB, and typically here, and leading by the current 90 degree. And now the potential difference between C is 1 upon 2 pi f c, that is OC, this one, and now the difference of these two will be your typically OD. So, represented by phasor OC lagging the current by 90 degree capacitive potential difference, and since OB and OC are in direct opposition. So, we can say resultant is OD, that is OB minus OC, and OB being assumed greater than OC. In this case, it may be reverse also. The supply voltage is then the phasor sum of OA and OD, namely the OE, that is the vector sum of this OA and OD. And we can say from this figure now OE square equal to OA square and OD square, that is OA square plus OB square minus the OC square, and that is equal to V square equal to R I square in bracket 2 pi f L I minus I upon 2 pi f c square. So, that we can say I equal to V upon under root in bracket R square plus 2 in bracket 2 pi f L minus 1 upon 2 pi f c square and under root of whole, where the z equal to V upon I equal to under root in bracket R square plus 2 pi f L minus 1 upon 2 pi f c square in bracket close, and that represents the phasor here. So, from this expression it can be seen that resultant reactance is 2 pi f L minus 1 upon 2 pi f c, or it can be said like x L minus x c, and if phi is the phase difference between the current and supply voltage. So, we can say tan phi is equal to A E upon O A or O D upon O A or O B minus O C upon O A, and that is 2 pi f L I minus I upon 2 pi f c upon R I, and you can say this, I mean I phi cancel out. So, you can say tan phi equal to x L minus x c upon R, and from this you can say cos phi equal to O A, typically O A divided by O E, and that is R I upon Z I, that is resistance and divided by impedance, and cos phi is R upon Z, and sin phi is A E upon O E, and that is sin phi is x upon Z. So, in the inductive, if the inductive reactance is greater than the capacitive reactance, then tan phi is positive and the current lags the supply voltage by an angle phi, and if tan phi is negative, signifying that the current leads the supply voltage by an angle phi, and note the case where x L equal to x c means that will become I equal to V upon R, because the drop of your reactance, both reactances will cancel out each other, they will be of opposite phase, and that we call it the resonance, you can call it the phenomena. Like now, coming to some of the numerical problems based on these circuits. So, a resistance of 7 ohm typically here is connected in series with the pure inductance of 31.8 millihenry, and the circuit is connected to 100 volt 50 hertz sinusoidal supply. Calculate the circuit current and the phase angle. So, here calculating the reactance x L equal to pi f L equal to pi into 50 into 31.8 into 10 power minus 3, because of convert to millihenry to henry, that becomes 10.0 ohm, and Z is here now R square plus x L square, under root of that becomes 7 square plus 10 square under root of this, that becomes 12.2 ohm. So, I will become V upon Z, that is 100 upon 12.2, that is 8.2 ampere, and the phi is tan inverse x L upon R, that is tan inverse 10 upon 7, and that is your 55.1 degree lag. So, coming to an example 2, a pure inductance of a 318 millihenry is connected in series with the pure resistance of 75 ohm. The circuit is supplied from a 50 hertz sinusoidal source, and the voltage across the 75 ohm resistance is found to be 150 volt. Calculate the supplied voltage. So, now here it is given that the resistance have a 150 volt. So, current from this we can find out V upon R, that is 150 by 75, that is 2 ampere. Now, we can say x L equal to pi f L, that is 2 pi 50 into 318 into 10 power minus 3, that is 100 ohm, and V I x L will be now 2 into 100, that is 200, and the voltage supply voltage will be now V square plus V L square under root of that. So, that is 150 square plus 200 square, under root of this will be 200 volt. So, now coming to the question 3, a coil having both resistance and inductance has a total effective impedance of 50 ohm, and the phase angle of the current through it with respect to the voltage across it is 45 degree lag, and the coil is connected in series with the 40 ohm resistance and across the sinusoidal supply, and the circuit current is 3 ampere. By conducting a Phasor diagram and estimate the supply voltage in the circuit lag. So, you have here typically resistance of 40 ohm and inductive reactance of typically you have 50 ohm. So, here you can call it like a you have a 3 ampere current here like. So, we can say V R equal to I R, that is 3 into 40, that is 120 volt, and V L R equal to I Z L R into 3 into 50, that is 150 volt. So, if we have been incorrect to write V L R equal to I Z, since Z is used to represent the total circuit impedance. So, if more complex problem than number used, so we can say Z 1, Z 2, Z 3 etc. In this example, such procedure will be little bit tedious. So, Phasor diagram is constructed by drawing the phasor of V R typically here, to some appropriate scale, and direction of this phasor will coincide with that of the current. Since the voltage across the coil will lead the current by 45 degree, voltage can also be drawn. So, complex or summation of two voltage given here V equal to 250 volt and phi equal to 25 degree. So, we can conclude the calculated solution is typically here V square equal to V square plus V L R square plus 2 V L R cos phi L R, and where V R equal to 120 square plus 150 square into 2 into 120 into 150 into 0.707, that is 62,500, and from this taking under root of this V equal to 250 volt, and we can find out cos phi will be equal to V R plus V L R cos phi L R divided by V, and that is 120 plus 150 into 0.07 divided by 250, that is 0.904, and phi is your 25 degree lag, considering the resistance of the inductive coil also in this circuit. So, coming to example 4, a 30 microfarad capacitor is connected across 400 volt 50 hertz supply. Calculate the reactance of capacitor, current in the capacitor. So, x equal to 1 upon 2 pi f c, we can calculate 2 into pi 3.14 into 50 into 30 into 10 power minus 6 to convert into microfarad into farad, and that becomes 106.2 ohm. And now, we can find out the typically the current, or you can call it V upon I is 1 upon 2 pi f c. So, from this we can find out the current, that V upon I, and this will be your 400 divided by 100 is 6.2, that is 3.6 ohm. Now, coming to fifth numerical problem, a capacitor of 8 microfarad takes a current of 1 ampere when the alternating voltage applied across it is 230 volt. Calculate, typically you have resistance, capacitance, and current is flowing 0.5 ampere with the 230 volt. So, first the frequency of applied voltage, the reactance resistance of the connected in series with the capacitor to reduce the current in the circuit to 0.5 ohm at the same frequency, and the phase angle of the resulting current. So, we have a capacitor known to us, and we know the current only pure capacitor is only 1 ohm. So, now what we are connecting resistance to reduce the current to half. Now, we can say x equal to V upon I, that is 230 upon 1. So, that is 230 ohm equal to pi f c. So, from which we can find out f c equal to 1 upon 2 pi f c into x c equal, and putting the value, that comes your 86.5 hertz. So, when the resistance is connected in series with the capacitor, the circuit is now given in V upon I, that is 230 upon 0.5. So, now impedance is 460 ohm, and that is R square plus X square under root of that, and we know the X c of 230 ohm. So, from this relation of we can find out R, which comes around 398 ohm, and we can find now phase angle cos inverse R. So, R upon Z, or cos inverse 398 upon 460, that comes 30 degree positive, means the you can call it the current is leading by 30 degree in this RC circuit. Now, coming to example 6, a coil of having a resistance of 12 ohm and an inductance of 0.1 Henry is connected across a 100 volt 50 hertz supply, and calculate the reactance and impedance of the coil, the current, phase difference between current and the applied voltage. So, now coming to with this, you have supply voltage of 100 volt 50 hertz with the resistance of 12 ohm and inductance of 0.1 Henry. So, it is not essential to draw the Phasor diagram to exact scale. So, coming with the calculation. So, reactance of the coil is X L, that is 2 pi F L equal to 2 pi into 50 into 0.1. So, that comes 31.4 ohm, and impedance is Z equal to under root R square plus X L square. So, you can put the value 12 square plus 31.4 square. So, that comes 33.6 ohm, and now current is I equal to V upon Z, that is 100 upon 33.6 equal to 2.97 ampere, and tan phi is x upon r, that is 31.4 by 12, that comes 2.617, and from which we can calculate the phi, that is equal to 69, phi equal to 69 degree, and that is the Phasor diagram of corresponding to the circuit here. Now, coming to example 7, a metal filament lamp rated at 750 watt 100 volt is to be connected in series with the capacitor across 230 volt 60 hertz supply. Calculate the capacitance required, the phase angle between the current and supply voltage, and now figure shows where R represents the lamp, and the phase diagram figure shows the VR across R is the phase with current I, while the voltage across the capacitor will lag by 90 degree. So, resultant voltage is the phasor sum of V L and V R from the diagram. I mean, you have a capacitor and you have a, and typically you have a 100 volt across. So, we can find out V square equal to V R square plus V C square. So, we have V R 100 volt and supply voltage 230. So, we can find out V C from here. So, V C square comes, I mean the value from which we can calculate the typically 270 volt. So, rated current of the lamp is your 750 watt divided by 100 volt, that is 7.5 ampere, and I upon V upon I will be 2 pi f c. So, now you can say 7.5 ampere will be your typically 2 pi into 3.14 into 60 into C into 207, and C comes from here 96 microfarad. So, if the phi is the phase angle between the current and supply voltage, so cos phi will be V R upon V, and that is 100 upon 230, that is 0.435, and from which we can calculate the phi equal to 64.12 degree. So, now example 8, a circuit having a resistance of 12 ohm, an inductance of 0.15 Henry and a capacitance of 100 microfarad in series is connected across a 100 volt 50 hertz supply. Calculate the impedance, then current, the voltage across RLC component and the phase difference between the voltage and current of the supply. So, coming to the solution, the circuit diagram the same of that. So, we can find out the impedance V upon I, that is I R square plus in 2 pi f L minus 2 pi f c square and root of that. So, keeping the value of all these of resistance 12 ohm square minus 2 into 3.14 into 50 into 0.15 Henry minus 10 to the power 6 into 2 into 3.14 into 10 50 into 100, and square of this and root of this total is come 19.4 ohm, and now current will be V upon Z, that is 100 upon 19.4, that is 5.15 ampere, and voltage across resistance is V R. So, that comes 12 into 5.15 equal to 61.8 volt, and voltage across inductor is your typically XL 40, typically 47.1 into 5.15, that is 242.5 volt. So, circuit diagram is the same that of here. So, the voltage across capacitor V C equal to 31.85 into 5.15 164 volt, and phase difference between the current and supply voltage will be now phi 47.1 minus 31.85 divided by 12, that is tan inverse 1.271, that is 51.48 degree. So, the now these are the unsolved problems. I mean some of the problem on the same line you can just solve that, and these are the references based on which we have this lecture and the problem, and thank you very much.